Good afternoon, this is Schweitzer and this is our introductory video on thermodynamics. First idea here is, what is energy? First things first is we have a couple of units of energy. Energy by definition is the ability to do work. Now in the average high school student, work means going to McDonald's, but in physics and chemistry, work is the essentially the amount of energy. It would be in unit of energy. And with energy you can do things like you can move things, cause things to move. You can take energy and convert it over to, let's say, potential energy. And there are lots of different forms of energy, and I'm not going to put them all down. One might be thermal or heat. So, in some sense, energy is the ability to do stuff. The most common unit of energy used in science is a joule. And a joule simply is defined as a Newton meter. And Newton is a unit of force, and a meter would be, well, a meter a distance. So applying a force to an item over the course of a meter is a joule. A calorie is another unit of energy, and this is the amount of energy needed to raise 1 gram of, I'm going to just put water, 1 degree Celsius. That is a calorie. Now, for purposes of a calorie, a calorie and a joule are related by the fact that 4.18 joules equals 1 calorie. Sometimes I'll refer to this as a chemical calorie. Because on packaging and whatnot, we'll have very often another unit of calories, which I call a commercial calorie. And it's distinguished by a capital C. And 1 big calorie equals 1,000 chemical calories. So, if you have 1 chemical calorie, 1 commercial calorie equals 1,000 chemical calories, which would equal 4,180 joules. Something to think about. Now, energy, when a chemical reaction takes place, can sometimes enter or exit, and we have these terms we call exothermic and endothermic. Two terms that we use would be system and surroundings. Now, one thing you want to understand is that you are in the surroundings. So if a system is exiting energy out towards you, a system could be simply a test tube, and it is radiating energy all around, and you are right next to it, so you feel that energy coming off and it feels warm. Anytime something feels warm, it's because the system's exiting energy towards you. This is exothermic. We quite often would look at this and say, okay, well, we have time here, and we have energy. And this is a drawing of called an energy diagram for a exothermic reaction. From here, this is the start, and this is the finish. Essentially, but they're both looking at the system as a whole. The system at the start, the system at the finish. So if we take a snapshot of the system when we first get going, this is how much energy it has right here. If we take a snapshot of, somehow we lost that. Let's drop back on here. At the end, it would look like this. So the difference from the start and the end would be this amount of energy right here. This is the amount of energy, sometimes referred to as Q, that is released. It's also at this point sometimes referred to as delta H. In fact, that's probably more common. It's the energy per cycle of the reaction. We'll talk more about delta H in a moment. Probably better to see this as delta H, but it is just energy being released. From the start to the peak, this energy right here is how much energy it takes to kick-start a reaction. That's energy of activation, or the activation energy. Every reaction requires a little bit of push to get started. If energy enters the system, then it will have to take it from the surroundings. We are in the surroundings. If the energy is not there, then it just isn't going to be there. It's going to be like wandering around the mall and having no money. You do nothing. So in this case, the energy has to be available, or just nothing takes place. This is the system before you start, and you need to absorb energy before anything will take place. This is the start, this is the end, and this is how much energy in the end we have gained. This is again more commonly referred to as delta H. Because the system's gaining energy, then this will be a positive. Unlike the last one, it will be a negative delta H. The energy of activation is still the start to the peak. Because energy is conserved, I can say that track the energy in the beginning, energy in the end. The difference between these two is my delta H. Energy is a quantifiable item. It's not changing. It's like having $100 in your pocket before you start the day. Got $50 in the end, therefore a net difference of 50. 50 is it's money. It's a hardcore item, and this is the conservation of energy. So that's the first law of thermodynamics: is energy is conserved. Another way to state that is energy cannot be created nor destroyed, simply converted from one form to another. Again, because it's not changing, we can track an item beforehand and say, okay, this item has a certain amount of X amount of energy, and if I could go through a process, some sort of chemical reaction, and take that same item, test it again, and say, okay, now this item has Y amount of energy. I say, okay, well then how much energy happened or exchanged during this particular process? Well, if energy entered the system, then Y should have greater amount of energy. If energy exited the system, then Y should have less energy. So what I do is I simply take Y minus X, and that gives me my change in energy, commonly referred to as delta H. We'll talk more about that later. Either way, this is a good start to the actual process here of introduction to energy. Thank you very much.